आज मेरा प्लान इज लाइक टू बिल्ड अपॉन बॉन्डिंग. जैसे मैंने लास्ट टाइम बात की थी, इफ यू हैव सीन द लेक्चर लास्ट टाइम का, मैंने बॉन्डिंग शुरू कर दिया था. आई एम अबाउट टू बिल्ड अपॉन की किस तरीके से होती है एंड अबाउट द elaborate on the ways that are important to us and are like at the heart of chemical bonding. So I'll be elaborating on that. पहले मैं कुछ on some notions I felt like I didn't elaborate much in the last lecture, so I'll be taking them up and reviewing a bit what I did in the last lecture. So in the initial few 15 to 20 minutes of the last lecture, I talked about stability and spontaneity. The point where I was not elaborate enough, I feel like, was the definition of stability in terms of energy. So I basically said this. And because I said it's a definition, you guys believed me. I hope you did. But the point is, we define things because we find them to be convenient and consistent with the rest of the stuff that we are dealing with. How do I know that this is convenient to me and consistent with everything that is around us? That is something that I'll elaborate with an example right now. So yeah, consider two bodies here. Say these are charged. I consider a positive charge here. I consider a positive charge here. I consider the distance to be r. What is the force these charged bodies, or if I consider them to be point charges or spherical bodies, what is the force they are exerting on each other? If this is say Q1 and this is Q2, what is the force they are exerting on each other? Yeah. It is defined by this equation. So now when I look at this essentially repels. This is essentially repelled by the other charge. So as goes for Newton's law, as we believe them right now, so this positively charged particle is going to go away. So R is going to increase in some sense. If this gets pushed away from this state, R is going to increase. And when I think of the expression of energy corresponding to this force, when I think about energy corresponding to this force, that is the electrostatic potential energy, that is the interaction between these two charges. That is given by. And now when I try to think about it, when R increases, energy decreases. And now if I come back to this picture, this charge going away is something that we observe, from the theory of charges. So this is something that we see that it happens actually. And when we compare it to the energy expression, we see energy becoming less. And as I told you guys that stability was our way initially to talk about why things are the way they are, and that is why this is the relationship that things should follow to be in the way they are, as you observe from this example. That is how we come to the notion that stability is inversely proportional to energy. That is how we find this definition of stability to be convenient to us and is really consistent with the rest of the stuff that we do. Now, this is something I myself wanted to elaborate on. Now I'll kind of review a bit of what else we studied in the last lecture. We talked about the notion of electronegativity in the last lecture. I told you guys about how the idea of electronegativity came up. I explained this to you by the example. When you think of common salt and when you put it into water, these molecules are going to homogeneously distribute throughout the solution, and this tells us that there is something that is pulling this away and there is something that is pulling this away. If these are being pulled away, there must be some force or agent driving that thing. What is doing that? There is only one thing except NaCl in the solution, that is water. But when we think about water, we don't think about charges. We don't think about actual charges. So what kind of charges do we invoke in order to make this theory consistent with the rest of the stuff that we are observing? We think of it as if one of the ends pulls more electron density towards it and the other end suffers a deficiency of electron density, then we see somewhat a charge development here and somewhat a charge development here. The same goes for the place here. That is how we come to the notion of electronegativity. And then we think about two charges being in the same entity. Physicists call this a dipole. And that's how we call these kind of molecules polar in nature. That is how electronegativity came up. Now we think about the consequences of electronegativity that I talked about. I talked about the example of the infamous Bend's rule. Not in its pure sense, like I didn't mention about S character and stuff because I have not built upon molecular orbital theory yet. So I didn't talk about it. We'll revisit this thing later in our series. So what I said was bond angle is directly proportional to the electronegativity of the central atom. What is the central atom? The thing that is essentially carrying all the other atoms in a molecule. So I'll call it Ca for now. Yeah. So how did we come up with this? Now I'll revisit it a bit. When we think about this electron density is kind of pushed towards oxygen because of its more electronegativity, and this bond suffers the same fate. Now, if we think about it, oxygen is not going to budge. Oxygen is constrained to be with H at both ends. So when these electrons come towards oxygen, they crowd the center. When they crowd the center, there is something that's got to minimize this repulsion. How do you minimize this repulsion? You kick these bonds a bit away. And as this electron density comes close and close to the center, these bonds are going to go away even more. Then we come to this notion that electronegativity of the central atom increases bond angle. And similar case was explored for px3. I came up with the data. You can refer to the previous lecture for that. I don't have the data right now. So yeah. So next what we talked about was the notion of, or rather the dichotomy of shielding and penetration. Talked about the dichotomy of shielding and penetration. I told you guys that penetration tells you about how close the location occupying an electron is to the nuclei. When you think about it in physical terms, although it's not very tangible or logical to do, how less this R is when we talk about an electron here, that denotes its penetration. How inwards, how penetrating an orbital is. Orbital, the place where an electron resides, is inside the atom. That is called the penetration effect. Now something being inside, that is interacting with the nuclei, and something being outside, when I consider a multi-electron system, something being outside, that is the inner electrons are affecting this interaction as well, because this R is less than R prime. The R prime that I told you, this R is less than this. And when we go back to Coulomb's law, this is attracted more than this. This kind of shields it, because these are repelling as well. If I say R double prime, these are repelling as well. So that gives us a notion of the inner electrons shielding the outside electrons. As I gave an example of a wall between me and shooting arrows at me. Yeah. The inner electrons essentially shield, the quote-unquote shielding effect that we talk about. That is a cause-effect relationship between penetration and shielding. After this, we talked about effective nuclear charge. This is quantified in a sense that this whole Z won't be felt by an outer electron because of the inter-electronic repulsions and the fact that this R is less than this R, that is R prime. So this Z actually reduces by a factor, and Slater came in and he he tried to empirically do it, because the reason for that is this R cannot be very accurately determined because of quantum effects. This R cannot be very accurately predicted, which is why Slater came in with some experimental considerations called Slater's rules, which are very mechanical in their nature, and you can easily compute stuff around effective nuclear charges for multi-electron systems.
Here the shielding is basically due to the inter-electronic repulsion and the penetration effect.
Yeah, primarily because of the penetration effect. Inter-electronic repulsions are a factor. They are indeed a factor, but the primal effect that is essentially driving this is penetration. The sub-electrons being much closer to the nuclei and some electrons being much farther away to the nuclei. And after this, we talked a bit about what a chemical bond is. This, to be honest, was thought of in my mind as the whole title of this series, which I was planning. But then it turns out that I had to complement it with the course as well. So I rather talk about the things that I talked about earlier as well. So yeah, I talked about a chemical bond. This is a drawing for future reference. When I talked about the chemical bond, when I talked about spontaneity and all, we talked in the factor of entropy that atoms move away from each other. Atoms tend to move away from each other in order to create disorder. But here, what if they come close to each other because of the electronic attraction between the nuclei of one atom and the electrons of the another atom? That essentially gives us the notion of a chemical bond. This A and this B, what if they don't go apart? What if they come close? What if they come close to this good old gap called the bond length? Why would they do this? You have a positive charge here, you have a positive charge here. Why would a positive charge come close to a positive charge? We are ignoring the fact that there are electrons too. These electrons are in between. This nuclei pulls these electrons close to it, the other nuclei pulls these electrons close to it, and this gap is the good old interplay between these two characters that are driving these atoms to come close, and hence we reach a very fine gap of what we call the bond length. And when physicists graph this, this turns out to be this. This is the state where this system of two atoms feels good enough to stay. That is, it is spontaneous for the system of atoms to stay in this state. We talk about this distance. I call it R. This is the bond length. By the initial notion of stability that we built, this is U0. This should be the global minimum. That is the minimum value for any value of R for this system. This should be minimum. So yeah, here is when we concluded. I talked about this Avogadro number thing as well. You can refer to the lecture for that. That's not very much relevant. Now the review, this chemical bond thing, there are essentially what is driving this? It's all electrostatic attraction. If I'm not, are you guys getting me? Only electrostatic attraction is what is driving this atoms coming close by. When we think about it, this attraction can be in two ways, principally in two ways. Either charge development, actual charge development happens, or actual charge development doesn't happen. This is something where we talk about our ionic bond. This is the point where we talk about the ionic bond. When actual charge development doesn't happen, we talk about something called a covalent bond. Either something loses electrons or it doesn't. There are only two possibilities here, which is why there are two possibilities of bonds. If you have heard of any other kind of bonds, they would most likely be the subsets of these, as I'll be talking about a few in a moment. So yeah, when we think about ionic bond, we think about actual charge development. We think about things like NAC. Things that break apart when you apply an electric field, things that interact with an electromagnetic radiation very directly. Think about actual charge development species. That is, in these the primal force of them being together is electrostatic attraction, which is when we talk about ionic bond. Now I'll come to the notion of when this happens and when this happens. I'll elaborate a lot more on this. This is actually the major thing that we study in chemical bonding. Yeah. So when I when I try to classify atoms that bond, I talk about something called a metal. When I go through the code of elements in periodic table, there are some things that lose electrons very easily. Some things that lose electrons very easily. And when we talk about things that gain electrons very easily, we call them non-metals. Now when I think of these two entities interacting with each other, this is the best model that I can come up with. This thing loses electrons, this thing gains electrons, and these two stay happily ever after with an ionic bond between them. Now, let's talk about the interaction between a metal and a non-metal and another non-metal. When we think about the interaction between a metal atom and another metal atom, what does a metal do? A metal loses electrons. Now, if a horde of metal atoms is together in a, say, you think of a bag or a box, if you think of a horde of metal atoms together, one of them loses electrons, another one that becomes positively charged. Maybe think of electrons being already present there from another metal losing them and there being a positive charge there. This electron and that M positive thing, these are going to interact with each other and form something that physicists call the electron C model. metals lose electrons and have an interaction solely based on solely based on charges of metals and electrons themselves. Then we talk about, then we call these positively charged metals as kernels. These kernels are going to interact with the lost electrons from other metal atoms. Then we think of this as, say, an M plus is here, an electron is here, an M plus is here, an M plus is here, an electron is here, and so on and so on. All the permutations you can think of. Chemists like to call this a metallic bond. Although I feel like this separate classification is not very much needed because it's solely based on charge development. The point that we use to define an ionic bond, there is no harm in calling this an ionic interaction as well. Just the historical context of it, that metals binding with metals is called a metallic bond, is the only reason that you hear this term. There is no other reason for that. So now, as we are clear with the interaction of one metal with another metal, let's think about the another combination that we talked about. The most interesting combination, in my opinion, and of all the people who have been involved in the formulation of all the theories that we study to this date, none of which is perfect, to be honest. Yeah, a non-metal and a non-metal interacting. It stems from the initial definition of chemical bond that I talked about. The interaction between the nucleus of one atom and the electrons of the another atom. One more factor is there, the mathematics of which is kind of complicated, which is why I am not invoking it. That is nuclear interaction. One nuclei also interacts with another nuclei. Two of the four fundamental physical forces are weak and strong nuclear forces, because of which also two atoms interact and attract each other to a certain limit, the graph of which is very similar to what we drew for a chemical bond. I am not invoking it just for the sake of the complicated mathematics that is involved, but that is also a very great factor, a great deal of a factor when we talk about the interaction between a non-metal atom and another non-metal atom. Now, because this thing is not losing electrons. This thing is made to gain electrons. But this guy is like, I won't lose electrons either. What do? They reach a middle ground. These two electrons, when these atoms come close because of their mutual interaction, electron, because of its inherent wave nature, when you think of as you have studied in the classical model of a wave, when you think of two waves coming close to each other, if I think of two waves coming close to each other, when their crests and troughs match, they kind of combine to give a larger amplitude of a wave. And when their crests and troughs don't match, they try to give something close to zero. Because if they exactly don't match, it would be zero. If they somewhat match, it would be something non-zero, but not very significant if they are not exactly interfering constructively. That is the terminology that we use when troughs and crests exactly match. We think of something called, I should write something. So we talk of constructive interaction of two waves. This interaction is explained by the phenomena called interference of waves. So, the contrary to this, when the crests and troughs don't match, we talk of something called destructive interaction or interference. Now, when these atoms are going to come close to each other, these atoms are going to come close to each other. These waves are also going to interact. When these interact, they will somewhat interact in a constructive fashion, somewhat interact in a destructive fashion, and they eventually end up being close for just for the sake of that Coulombic factor that we talked about, and also the nuclear interactions. This is how we talk of the most interesting bond in all chemistry, that is a covalent bond. The center of all chemistry for around, primary 100 to 200 years of the advent of chemistry was the discussion about the covalent bond. Was of this non-deterministic and deterministic way of seeing quantum mechanics or quantum physics that is involved here. Electron being a wave is a very counterintuitive kind of thing for somebody to believe who has been made to think of electron as a particle initially. It is very difficult to make somebody believe and also theorize everything after that accordingly. Now, when we talk about the covalent bond, you must have heard of another fashions of covalent bond as well. I'll talk about it. Maybe let's just quote it for now. You must have heard of a coordinate bond. But as I said, there are only two kind of bonds that form. One is ionic and another is covalent. All other of them are just subforms of these two. This essentially is one atom giving electrons to another atom that is deficient of a pair of electrons, and both of them sharing that pair of electrons between them, which essentially behaves like a covalent bond only at the end. This is something that we'll talk a lot about after we are done with the basic notion of chemical bonding. We'll talk a lot about coordinate covalent bonds later. Now let's talk about the covalent bond in general. People came in and as they had some notion of how the things where electrons are looked, they thought they knew how orbitals looked because of their mathematical calculations. They knew how orbitals looked, and I'll revisit that for you guys. This is weird. You guys know about it. I'll draw it when I show its bonding. So this is how they drew it. And now another thing that we talk about in the case of interaction that I didn't tell you is, because these are waves, something called phase for a wave, that component of that. This thing that you see in an equation of wave, it keeps on changing with time. This thing keeps on changing with time. You see a wave at one instant, you see a wave at another instant. It is not at the same position in terms of its propagation. So then we talk about phases. When we talk about phases, we think of phases in these orbitals, because these are essentially superposed waves. These are also regions where those waves reside. So when we think about it, we think about to just maybe talk of the relative configuration, that one orbital is going to combine with another orbital eventually. To talk about the relative configuration, we define phases to be either plus or minus for a loop. This plus and minus is completely arbitrary. When we this was done only for the sake of some orbital having multiple lobes, as we see here. This is you call these balloons as lobes that I'm showing you right now. Yeah. So just because of these, we had to think about two phase indicators so that we could show that these only interact in a certain fashion and not any other fashion. That also tells us about the directionality of a covalent bond. You need that omega T thing to match for both of them for them to bond, and that omega T thing to mismatch for both of them to not bond, rather not bond. We will talk about what happens then as well, but that's a lot later. When we think about this, we see either plus or minus. When I talk specifically about S, it doesn't matter what you call it, it's all symmetrical. You can call it plus at one instant and minus at another instant. But when two of them combine, when two s orbitals are going to combine, they are going to combine only when this is plus. Say I call it S1 and I call this S2. If this has to combine with this has to be plus. If this is minus and this is minus, there is no issue with them overlapping. But if this thing becomes plus and this thing becomes minus, there is an issue with them overlapping. That is the condition for them to overlap. And when they don't overlap, we call it a zero overlap. We call it a zero overlap. And I did tell you, but I started talking about how chemists thought of bonding initially, and they kind of named it something which I didn't tell you about earlier. They called it the valence bond theory. Now, as said, s orbitals are combining, but there are many s orbitals inside an atom. Which s orbitals are we talking about? As we talked about penetration, some orbitals are way closer to the nuclei for them to have a significant interaction with the electrons of some other nuclei, which kind of binds them from interacting with another nuclei, which is why the only pairs of electrons that are going to combine should be energetically high enough or maybe farther away from the nucleus of the atom for them to combine with another atom's electrons. That's when we invoke the notion of valence electrons. What are valence electrons? The electrons that reside in orbitals with a principal quantum number quantum number that is the highest possible for that atom, because the inner ones are going to get shielded by these pair of electrons. So the ones that are going to bond are essentially the ones with the highest possible principal quantum number, which we denote by the letter N, as seen a lot before. Now I purposefully ignored something that I talked about earlier. I never talked about this. I said it's a zero overlap. They don't overlap. But what does happen to those orbitals after this destructive kind of thing happens? What happens to those electrons? Where do they go? That is something that was a very primal drawback of the valence bond theory, was they never talked about when destructive interference happens. Where do those electrons go? Where does that cloud go? Does it stop existing? No, it does not. That is something that is talked about later. So here we are almost done with valence bond theory. After I talk about the intricacies of the p orbital overlapping and d orbital overlapping. I know this might seem boring, but please do ask questions. Don't feel that your questions are dumb, please. Please do ask questions. Any questions that you might have hesitated to ask to your school teacher or a coaching teacher, because they kind of demean people a lot. So yeah, where was I? I was talking about overlapping by so I was talking about p orbital overlapping. How does a p orbital look? I just showed you. When we think about those nuclei that we were considering, if the axis about which they are combining, if the p orbital is along that axis, it looks like this. It looks like this. This is the axis at which they are combining, which I call the internuclear axis. Which chemists like to call it Z, which is not at all a necessity. You guys might call it X, you guys might call it Y, you guys might convert this to polar coordinates as Amir Ashraf told you, that doesn't matter. Now, when I talk about phases, I talk about these plus and minus things. Now, this is all mathematically calculated. When you think of loops, these have to kind of cancel each other so that this thing remains stabilized. This is all a mathematical construct for us to explain the behavior of these p orbitals overlapping with each other. This is all a construct. This is not something that we see. Now, when another call this X or Y, call this X or Y. When these two orbitals are going to come close to each other, what condition do we have for these things to combine now? This row faces this row. What condition, according to what the classical valence bond theory, the notion that it gives us, what condition do we need for this row to combine with this row? Or maybe this row to combine with this row, because when we flip these, this is going to face this row. What condition do we have for them to combine?
Same alignment.
Same alignment. In what sense?
Same internuclear axis.
Same internuclear axis is something that is given. We need this thing to match this thing in terms of that omega t term, because these are going to combine constructively as we talked about. And as for now, we are ignoring that destructive interference factor as the chemists initially did, and theories improved from there as well. But this also gives us an idea for the electrons to come between atoms essentially. How do they stay there? So this plus thing got to match this plus thing for these two to combine, and when this is plus, symmetrically this should be minus. Now this symmetry is something that comes out of the construct of these orbitals mathematically. So now when I let me show it equivalently as well. So when I talk about this Z, when these orbitals combine, because these are constructively combining, this thing will raise its amplitude. What is the amplitude in our case? The amplitude is this cloud of electrons that is as large as the amplitude is. The size of the cloud depends upon the amplitude of the wave that this orbital corresponds to. When we think about it, this thing is now going to increase. This thing increases minus, plus. This thing increases its amplitude, and these remain here because the electron density shifts from here to here, a bit of it shifts from here to here. Not essentially shifting, its relative enlargement of these combining lobes. This is when two orbitals combine along the internuclear axis. We call it sigma bonding. The Greek letter sigma is used to denote this kind of overlapping. But from mathematical constructs, as we know, this thing this thing might even exist. This thing might exist as this as well. This thing might exist along x and y as well. What happens when we try to combine these? When you think about it, none of these lobes align. None of these lobes align well enough for for these two to combine and give a bigger lobe, as we think of in terms of the classical valence bond theory idea that we have. None of these lobes fulfill that idea, for the sole reason of this thing having no electrons, because here there is no enlargement of that cloud that we mathematically constructed. There are no electrons. We call these points as nodes, if I didn't mention earlier. These points are called nodes. There are no electrons are present here. So these two cannot combine because they are not in a proper alignment for them to combine. This is something. The axis that we considered, we call this PZ, this orbital PZ, because it's along the z-axis as we conventionally consider. And we call this either px when it is along px or along the x-axis, and you call this py when it's along the y-axis. Now, as these two are not going to overlap ever again, or they didn't overlap to begin with, what do we call this? In the classical valence bond theory idea, we call this a zero overlap. We call this a zero overlap. But what if I do something to change this? If I do something to make these two align with each other so that they cannot combine. As you can see, this lobe is somewhat in the clear alignment of this lobe, that these electron densities can come close to each other. But in the other case, here was a node and here was electron density. A node cannot interact with electron density. There is no driving force for that. Now, these two electron densities can potentially overlap with each other, but they are not exactly coming towards each other. They are kind of going towards each other for the nuclear attraction, but a small part of it is attracted and a small part of it is interacting, not the whole loop. Here we talk about something called as pi bonding. And as somebody was murmuring, it's called sidewise overlapping, because these are overlapping sideways. And for sigma bonding, I didn't mention, it is called head-on overlapping. Head-on overlapping, as they are kind of, these terms are just to explain this physical sense of these orbitals combining. They kind of combine with the, if you think of those nodes as heads, they kind of combine with each other's heads, they bang into each other's heads. Yeah. So when I talk about these things combining, some of this combines with some of this. But as I said, it's not necessary for phases to be just positive for electron densities to combine. They can be negative as well. They just have to be the same. They have to be relatively the same for those electron clouds to combine. This negative portion can also combine with this negative portion. So then we see this is not a good one. Now, when we think of the resultant of this, think of the resultant of this. covalent of these two, the drawing is kind of weird, but I hope you get the point. This is around the axis. These combining clouds are around the axis, and these things would be enlarged when compared to these. When compared to these side lobes, these middle things would be enlarged because they are overlapped constructively. And this, my friends, is called the classic ion. Now, this very notion is when quantum mechanics and quantum physics was coming up, when we were thinking of electrons as waves, this is something that came straight to the mind of chemists or say physicists as well. This came straight to their mind, but then came drawbacks, as I talked about. Then they had to improve their theories a bit in order to accommodate for evidences that they gathered that don't follow this pattern. Now, when we think about the drawbacks of valence bond theory, one drawback was that I talked about initially. It doesn't think about destructive interference. It doesn't even think about destructive interference. And now, when I think about the second drawback, if you have heard of those crystallography equipments or spectroscopy instruments that are used to determine bond parameters like bond angle, bond length, then you use them, you use techniques to measure those parameters. You see that when say something A is connected to something B, like this symmetrically, or let me just consider one more. Just for the sake of showing them, if I think of it, if say A has some s orbital, some px, some py, some pz. A has these orbitals. In order to combine with those B ends, B offers the same orbital each time, but A offers different orbitals each time. And when we think about those diagrams that we just drew, the overlapping in these cases is strikingly different. When we see about the physical significance, the overlapping in these cases is strikingly different. So when we check about these bond parameters, we expect these bonds to be different in accordance to these overlapping extents. But what we see is that all of these bonds are the same. This thing was addressed before this. Maybe this was addressed as well, but the theory that we are going to talk about right now doesn't essentially address this. Doesn't very much address this drawback of it. When we think about it, if I have to rationalize this fact that these bonds are the same, even though the orbitals are different, the most plausible argument that I can make is that these orbitals, if they are combining, they combine the same way, but they combine in a way that they form different orbitals that are of the same energy. Then, if the energy differences and the symmetries are the same, then we can think of these bonds as identical. Then comes in the idea of hybridization, which is in itself very much flawed when we will be talking about coordinate covalent bonding. This thing is very, very much flawed and used extensively, but it is not very logical to do so. But for now, to address this discrepancy, this works well enough. The the molecule that was initially observed for this was the good old methane, the good old biogas. So also there is a very what do you say a question, a very fundamental question that is ingrained in you from the starting. Why is methane tetrahedral? You got to search about it. Why is methane exactly tetrahedral? One factor is that these hydrogen atoms repel each other, and the most optimal configuration that they can come in is a tetrahedron. But there could be some other configurations as well. They could have become like this. They could have become like this in the same plane. Why did they become like this? This is a question that you got to find the answer to. I cannot guarantee you a treat. I broke myself. So yeah. So why is methane tetrahedral? This is something that I want to answer. So yeah. For now, when we talk about hybridization, what orbitals does carbon have to offer to hydrogens to overlap? When we write the electronic configuration of carbon, so we write this. This thing is not of our use because this is not the highest n. We need the orbitals with the highest n or the principal quantum number. So this is something we are interested in. Now when we think about it, we have this orbital, we have this orbital, we have this orbital, we have this orbital. We have enough orbitals in order to form these bonds. But are they all equivalent? They are not. But in what do you say, a mathematical sense, if I were to make them equivalent, we can combine these wave functions mathematically and spit out a wave function that which when multiplied by 4 represents the sum of all these orbitals. Now, when we come to that, we need to understand that we need to make these orbitals same as well. These orbitals are not the same in themselves as well. This is fully filled. This is something that has one electron. It should have two. It has one electron. It should have two. I mean, not should have, but for it to be filled, it should have two. This thing is empty. So, in order to make them equivalent, what do you do is the gaps in these orbitals, the energy gaps in these orbitals are not very much, not very high. So when you say, I will invoke some thermodynamics here, when you are making A to B and B to C, when you need to make A to C and you have to go from A to B first, you need some positive energy input, and here something is getting released. So for this thing to be spontaneous, for this thing to go by itself, this negative thing should be much more by the stability notion that we drew earlier. This thing should be more than this, so that this negative thing can compensate for this initial push that we are assuming that is given to the molecule in order to form. This thing compensates for that, and when we actually try to make them equivalent, we push this electron here. It takes some energy, but that energy, much more than that energy, gets released when these things combine with the orbitals from orbitals from H. So when we hit this electron here, and you have 4 identical orbitals. Now, for just rotational purposes, we For this rotational purposes, we need to give names to these orbitals somehow. This was initially an S, but it is no more an S because it has one less electron than the initial S that we had. It has less interelectronic repulsions. It might have reduced in energy in its own sense. So it is not the same orbital after all. So we need to give some name to these orbitals. We have one S from here combining. We have three p orbitals from here combining. We have three p orbitals from here combining. And we add these two, we call it, you might call it 3sp, but chemists are weird. They put this in here. I don't know why. So you call these orbitals as sp3. And the term for this that is used is for this phenomena that we are talking about. This is not exactly a phenomena. This is a purely mathematical construction to explain this. No hybridization actually happens. This is something that we construct in order to explain the data that we have. We have no evidence for this thing to happen. We are trying to theorize it somehow. So that is how we have the notion of these orbitals, which are as they are the results of this so-called phenomena called hybridization. We call them hybrid orbitals. And now all of them are good enough and equivalent in energy. As I talked about, these wave functions are now converted into other equivalent wave functions, that the sum of these all becomes equal to one of these times 4, which is the same, which essentially makes all of these bonds equivalent, which was essentially our purpose in order to say rationalize our observation. So now when this sp3 electron, this combines this electron, this interacts with the electron from hydrogen as 1s1. It has s orbital. When these orbitals interact with each other constructively, they form this bond, they form this bond, they form this bond, and they form this bond. Then we have the good old CH4. That is how we explain. That is how we explain why these bonds are equivalent. And I'm reiterating again and again, hybridization is not something that actually happens. Hybridization is just a mathematical construct to rationalize our observations. Now we'll revisit the notion of bond angles again when we talk of these bonds. The reason these are far apart is because electrons repel due to the Coulomb's force that we talked about, and is very established. These electrons go far away from each other just for that fact, and the configuration in which they stay is because of this repulsion only. Then when we think about this repulsion affecting this angle in some sense, we talk about a theory or a principle that we call VSEPR. I don't know why chemists acronyms, but they would have just called it this. Valence shell, electron, repulsion. Now, a natural question that should come to your mind is, why why just valence shell electrons? Don't the electrons that are not in the valence shell, that are much inside and closer to the nuclei, why don't they repel? They do repel. But the point is that when these two nuclei come close to each other and the two atoms have to bond, the electrons that are at the least distance from each other are the valence electrons only, and the inner electrons are inner enough for them to not interact with the outer electrons because of the penetration effect that we talked about. Hence, the stress over valence shell electrons rather than the electrons that we call non-bonding. This also becomes prevalent at some cases. Then we talk about their repulsion as well, but that is something that is very niche and is applicable to a few examples only. And it's better to think of such advanced examples in terms of molecular orbital theory only, rather than trying to use the rationale that's just a mathematical construct and not consistent with one of the drawbacks that we earlier discussed. So I'd rather not discuss this one now. So yeah, there we have valence shell electron pair repulsion. So these pairs of electrons, when they are at some distance from each other, they do repel, but they go far apart enough for them to stay in the stable state that they are, the state of minimum repulsion that they are, the good old gap. We call this the bond angle. So this repulsion is something that gets minimized as a molecule forms. But when we think about, we have some of the molecules that have pairs of electrons in the valence shell itself, but they are not bonding because of the lack of these side atoms. They are not at all bonding. You don't see say H4O. There are multiple reasons for that, and then we are not focused on them for now. We call these the lone pairs. The lone pairs of electrons. These are something that we call, but these are bonded, so we call them bond pairs of electrons. And now, if you think about it, these are farther apart enough by construction of the molecule. But these guys, they don't care because they are not bonded. They are centralized on this atom. So they are the ones that are freer to move than bond pairs. So when these come along, they would be like, go away. Why doesn't this bond go away? Why doesn't this bond collapse into this one? Because here is, by construction, these were at some distance, and if this pushes it a bit, they are not going to collide. The electrons are not going to combine. They are still separate electron clouds. So when this thing repels it, it's much more than when these things repel. When we talk about the repulsion between these two things, the reason for which is that these were far apart enough by construction, by the observations that we already made. We did observe these initially, and these are freer enough because they are not constrained to stay between two atoms. And now, when we see these atoms repelling, then we talk about the fact that bond pairs, when they repel when bond pairs repel with bond pairs, that is much lesser than when bond pairs repel with lone pairs. These these guys are much freer than these guys. Yeah. And when two free guys are going to collide, free guys are going to interact, they are not constrained. Neither of these is constrained to stay at any position. They are they can be let's say distributed about the sphere of the atom. They could be anywhere, so they repel the most. That is when we come to the notion of this lone pair interaction. This being the maximum, because here are one free guy and one constrained guy interacting, and here are two free guys interacting. That is why we come up with this relation that we sometimes think for granted. And this is much like the essence of the valential electron repulsion that we are talking about. This can be used to rationalize facts like, say, for a tetrahedron, for an equilateral tetrahedron, for all the angles to be same, the angle has to be around 109 point, say, I don't know, it was 109.5 or something, I don't remember. Yeah, this is somewhat the angle that has to stay, but the water molecule, when you check its bond angle, it's much lesser than that. It's around 100 degrees, if I'm not wrong, it is around 100 degrees, which is much lesser than that. When you can think of these lone pairs repelling each other, and these lone pairs repelling the bond pairs consequentially, and these bond pairs get squished inside. That is why this 100-degree thing comes in. So that's how you can rationalize the bond angles deviating from the ideal geometry that we think of when all of the pairs are bonded. And those geometries that we talked about, that is something that is very mechanical to think about, because that's based on the repulsion being minimized. And you all know pentagonal parameter and all that, so I don't want to bore you guys with that. I just wanted to give you an intuition as to why all that happens. That is all lying in the notion of valential electron pair repulsion. So that is all for today. Essentially, I'll be talking about how this thing fails to explain the first drawback that we talked about. That is of destructive interference. That is the most modern theory that we'll talk about in the next class, and molecular quantum theory. And as risky as chemistry gets, even this is not the perfect theory that we have until now, as risky as it gets. So it's up to us maybe that you guys and me, that we can think of something that is better than this. In my personal opinion, we'd never be able to reach a perfect theory in any sense, because there will always be deviations from what we think about, because we can only think so much. We cannot think about everything at the same time. The problem with chemistry is that you have to deal with all the variables at the same time. When you think about physics, you think about one variable at a time, keeping everything else constant. When you think about chemistry, you cannot do that because you are observing everything. So all the variables come in handy at the same time. That is what makes it difficult for us to think of a perfect bonding theory, for which we kind of despise the discipline of chemistry, that we don't have a single theory that explains everything. In my opinion, there can't be. We should rather accept the fact and move on with it. That's all with which I will conclude this lecture. Thanks.